So with this further projectile motion, and of course it used to be in the old Extension 1 course, so I thought I'd just look at one of the more interesting Extension 1s. Came from 2014, and so we've got this ski jumper and landing on a slope. So actually ends up landing below the horizontal in this one. So you know, all the usual conditions are given to us, and they've told us the displacement equations for both the x and the y direction. First thing was to simply just come up with the Cartesian equation. So that's where we use our parametrics. We've got to eliminate the t, substitute it in. So if I look at x, t will be x over v cos theta. Substitute that in for the y, and now we just need to manipulate this to get it in the form that they've requested. So sine on cos is tan, we've got that. The reciprocal of cos is sec, so we've got our sec squared, and we come up with, was that the result they wanted? Oh no. Ah well, it was the result they wanted, but they had it the other way around, so all right, I swapped the terms around to make it look like what they wanted. Show that d, and what was d again? D is the distance down that slope. So that's what we've got to work out. So we should end up with this expression. So all right. Now I'm using the ratio of y over x to do something here. So I've said the y value over the x value. Now that has the advantage there of, I know that angle is 45 degrees. They told me that. So the tan of negative, because it was below, negative pi on 4 would be that expression. So tan of negative pi on 4 is of course negative 1. So playing around with this, I end up with an expression for the time it takes for it to land. Now, I discounted one of them because obviously t equals 0 is a solution as well. Well, that's where it's starting, because it's starting from that slope as well. So it's the other one I want. So 2v on g sine theta plus cos theta. Okay, bit of trig. I can work out that d is the square root of 2 times x. But x, we said, was vt cos theta. Substitute in what we just worked out for t, and it comes out quite nicely. There's our expression. So you can see a little bit more involved than a standard projectile motion question. You've really got to think about that one. How on earth are we going to get this answer? Well, then they want us to work out the d, the theta. Well, that's fine. The only pronumeral in the other one is theta, because the others are constants. So it's just straight differentiation. There's d. I'm going to expand it out rather than using the product rule, because cos theta sine theta, I can rewrite into a half sine 2 theta. I didn't worry about the second one, because when I differentiate the second one, look what I get. I get minus 2 cos theta sine theta. Now I can use the double angle result, and we get the sine 2 theta into our expression. Show that d has a maximum value and find the value for theta. Okay, so there's d, playing around with it. So now I've got the double angles in there again. So sine 2 theta plus cos 2 theta plus 1. That becomes cos 2 theta minus pi on 4. How did I get that? Well, auxiliary angle. Forget about the plus 1 there, because the plus 1 is how I got that last term there, the root t v squared on g. But I've got sine 2 theta plus cos 2 theta, which I can recombine into one trig term. So I've got cos 2 theta minus pi on 4. Well, why did I do that? Well, now it's a single trig value. It's very easy to find its maximum or minimum. Okay, so we know that the cos of 2 theta minus pi on 4 is a maximum when that is equal to 0. In other words, theta is pi on 8. They probably weren't expecting me to do that, because remember in part C we found that derivative? They were probably expecting me to find stationary points and do all that. But, you know, they didn't specify which way to do it. I just thought it's easier to look at the trig function rather than use calculus on that. I love this question. The bird question. Dumb bird. A stone is thrown so that it's going to hit a bird sitting at the top of a pole. But the bird sees that you're throwing a stone at it and decides to fly away. And it flies away in a horizontal straight line at a speed of 10 meters per second. The stone reaches height double that of the pole, and in its descent, I still hit the bird anyway. Dumb bird. Should have flown towards me, not away from me. Okay. Find the horizontal component of the velocity of the stone. Now I'm assuming there's no air resistance. They haven't told me anything about it in this question. So I know the projectile will be a parabola. Right? The stone's going to arc a parabola. So I'm actually going to use quadratics rather than calculus to solve this problem. The greatest height will occur at the vertex of the parabola. So I'm going to let the coordinates of that vertex be 0 to h, because it was twice the height of the pole. That means the equation of my parabola will be 2h minus kx squared. I've got a parabola, upside down parabola, shifting it up, 2h. It looks something like that. So there's the pole, and the bird's flying along that black line there. Now when y equals h, I'm interested to find out the x value there. So if that's the equation of the parabola, h will be 2h minus kx squared, giving me that x is plus or minus the square root of h on k. That first point where the bird is sitting is the coordinates minus root h on k h, and where it gets hit will be positive root h on k h. So the bird ends up flying a total distance of 2 root h on k meters at 10 meters per second. Well, speed equals distance over time, therefore time equals distance over speed, and we get the time being 1/5 root h on k. Now, when y equals 0 equals 2h minus kx squared, the way I've set mine up. So therefore, x squared equals 2h on k, so x is plus or minus the square root of 2h on k. So that point over there is negative root 2h on k, but the rock travels a distance then, here we go, I've thrown the rock from minus root 2h on k. So the rock has travelled horizontally, root 2h on k plus another root h on k that the bird has flown. There we go. So that's how far it has travelled horizontally. Speed equals distance over time. Actually, my k's end up cancelling out. And there's the horizontal velocity of the stone. A different way of solving the problem, just not using calculus, just using the quadratic to do it. The interesting thing it mentions in the syllabus is looking at projectile motion with air resistance. So it changes it. It's no longer, you can see the picture there, it's no longer a parabola. It's got a bit of a distortion. Now the only time a question on this has happened in the HSC was way back in 2003. So let's have a look at that question. They've given us the two equations. So you'll notice no longer is horizontal acceleration 0 because it's now got resistance in the opposite direction. And the vertical one still has gravity, of course, but again now has resistance as well. Derive this result. There's the horizontal velocity. Okay, so dx dot dt is minus kx dot. So separate my variables. Well, on the left I've gone straight to t equals because I know I'm going to get integral of 0 to t dt. But I've got minus 1 on k, the integral dx dot on x dot of u cos alpha, and it's x dot we're trying to find. Well, that's a log function. Substitute in. Now there's an expression for t, but we want to make x dot the subject. So moving the k over, exponentializing, we get the expression that they wanted. This is possibly where I misread the question. Part B says verify it satisfies. So actually all I really needed to do was differentiate it and shows it satisfies the equation. But I decided to derive it rather than verify it. So I've gone through the whole process again. dy dot dt is minus ky. Same process. Separate my variables. Substitute in. There's an expression for, well, kt. We want to make y dot the subject, and I end up with what they've asked. Possibly took a bit more time. However, it turned out to be a good mistake because it made part C quicker. Find the value of t when the particle reaches its maximum height. Well, maximum height still occurs when it's equal to 0. So now I can go back to what I'd already worked out. Because of the way I did it, I've got an expression for t. See, u sine alpha going up to y dot. But in this one, y dot is now 0. So I can use that result I got before. So subbing in, and I get it quite quickly. So it was a serendipitous mistake. What is the limiting value of the horizontal displacement? So we need to come up with an expression for horizontal displacement. X will be the limit as t approaches infinity of u cos alpha, the integral of e to the minus kt dt. Substituting in, we get e minus e to the minus kt plus 1, backwards exponential, that approaches 0, therefore x will be u cos alpha on k. But as I say, that was the only one they've ever asked involving resistive motion and projectile motion. It's an interesting thing to put in the syllabus because now what else can they ask? It's the only situation you can have. So they've already asked it. Ooh, they're going to ask it again? Who knows? So what have they asked? Here's last year's one. It was a 5-marker and it wasn't in parts. You basically had to put it all together yourself. So it's the standard sort of projectile motion. They put a nice little picture there for you to look at, and they've given us the displacement, but they've given it as a position vector. For some values of theta, there will be 2 times during the flight when the particle's position vector is perpendicular to its velocity vector. Find the values of theta for which this occurs, justifying that both times occur during the time of flight. Well, there is our displacement, or position vector. We differentiate it, we can get a velocity vector. But we're saying the position vector is perpendicular to its velocity vector. So the dot product must equal 0. We end up with this beautiful expression. All right, so tidying that up, here is our equation. That's got to equal 0. Well, you'll notice there's a common factor of t in there, but t has to be greater than 0 because it's during the time of flight. So I can divide through by t to end up with a quadratic. G squared t squared minus 3 gut sine theta plus 2u squared. Okay, as there are 2 distinct times this happens, okay, because it's saying for some values of theta there will be 2 times. So if there's 2 times, the discriminant of that quadratic, so you don't actually have to solve it straight away. I can just look at the discriminant, that's got to be greater than 0. That ends up with sine squared theta is greater than 8 on 9. Thus, sine squared must be in between 8 on 9 and 1, because it can't be bigger than 1. Theta is an acute angle as well. That's the other thing we know. So because it's acute, then root 8 on 9 must be less than sine theta is less than, why did I write 90 degrees there? That's a typo. That should still be 1, of course. So sine theta is less than 1. Okay? Got to be positive. It's acute. Now I can find the angle. Well, I didn't find the angle on the left-hand side straight away. I just said, well, that's going to be the inverse sine of 2 root 2 on 3. It's going to be in between that and 90. So theta must be in between 71 degrees and 90 degrees. Now, a lot of people stop there. They say, oh, look, I've got 2 values. But of course, it said, not only find them, justify that both of those times occur during the time of flight. Well, I know the particle hits the ground when y equals 0, so I need to find out the time of flight. Solving that one, we get t is 2u sine theta on g. So both values of theta must occur between time being 0 and 2u sine theta on g. Got to occur between there for this to work. Okay, let's go back to the equation and actually try and solve it. T is 3u sine theta plus or minus u root 9 sine squared theta minus 8 over 2g. 3u sine theta minus u root 9 sine squared theta minus 8 must be greater than 3u sine theta minus u root 9 sine squared theta. Because in the second one, I'm taking more away. Well, look at the second one. 3u sine theta minus the square root of 9 sine squared theta is 3 sine theta. So that is 0. So both times are greater than 0. Because I just worked out that the negative one is greater than 0. Well, clearly the plus one has to be greater than 0 as well. So all right, I've got positive times. That's good. Well, what's the largest value? Because remember, we want to show it's in between 0 and 2u sine theta on g. So what's the largest one? Well, the largest one would be t equals 3u sine theta plus u minus 8. Well, that's going to be less than, and in the square root sign there, I've rewritten that as minus 8 sine squared theta. Because 8 sine squared theta, well, the biggest it could be is 1. So therefore, all the others must be less than that amount. Well, that means that t is less than this expression, 2u sine theta on g. Hang on, t has to be in between. So both times do occur within the time of flight. So there we go. We know theta has to be in between 71 and 90 degrees, and I have justified that they occur. Okay. There you go.